Design of concrete structures. Let's solve another example in T-shaped beam analysis. So in this example, we have a problem like a T-shaped section with the effective depths, effective width of flange of 28 inches, height of flange of 6 inches, and like with a 6 tensile rebars, each number 10. So as you can see here, two groups of rebar at the tensile domain consist of 6 number 10 rebars, and the distance of 4 inch from the bottom of the section, that's a coverage for that, and BW is 10 inches. Its of web is 10 inches. Specific strength of concrete, a 3,000 pound square inches, and yield strength of steel is 60,000 psi. Let's approach the problem. T-shaped section, the very T-shaped section analysis, the very first step is calculation the depths of thickness block and make a comparison of that to height of flange. So if you remember, we just consider the whole section like a solid rectangular section with the effective depths and effective widths of flange. So this is the dimension, effective width of the flange and effective depth to the center from the top of the section to the center of tensile rebar at the bottom of the section. So then calculate A like a just for a simple rectangular section, that's AS times Fy over 85 percentile of F prime C times B, which is, you can just simply replace that B effective because this is all rectangular section. And then make a comparison with HF, and if your B, if your A, your height of this block, for example, it's here, it's not entering, it's less than HF, there is no need for T-shaped calculation because your A is just stop somewhere in the flange and it doesn't enter to the domain of webs. So there is no need to calculate the T-shaped cross section. But if your A is entering the domain of A, so it means A is bigger than height of flange, we are already entered to the domain of web. So definitely we do need to have an analysis based off a T-shaped section. Let's see what is our case here. So if you calculate the base of that, so definitely area for steel number 10, rebar number 10 is 1.27 inches square. And if we have definitely 6 of them, that's 6 times 127, and it just make it like 7.62 inches squared. If you just replace that in your area of steel times Fy, we just, this is 60,000 over 3,000, so we just simplify that. 85% over 85% times 28, which is B effective. It just gives us A is 6.40. The second, so it's definitely bigger than AH, height of flange, H of F. So we do need to go for a 6.4 is bigger than 6. Definitely we do need the T-shape analysis. If you remember the T-shape analysis of the sections, the concrete section, it's very similar to double reinforced concrete section, which we have solved them over and over. So we dissect the section like a two-part. So this is the thickness block distribution, that's A, this is C, X, which is equal to central, and we just dissect it to parts. So one is responsible for the flange, and the other part is responsible for the web part. So we can easily see the stresses and also forces for that. So in that case, we can dissect also the moment like MR, M. Also, MR is equal to nominal moment. Some in books show them in different formats. So M sub N or M sub R are the same. So we can say MN for flange part, these are the same equivalent to each other. Mn for flange. That's ASF times Fy times the arm. So this is our force times arm. They give us a moment related to the flange part. That's equal to the other force in concrete, which the only unknown in this equation is a area of steel for flange. So if you just make these two equal to each other, it just gives you what area of steel for flange is. If you replace that in the equation, so and the other part is mr. As soon as you have your area of steel for flange, you can just have it like subtract it from the tensile domain, like what we have in the double reinforced AS1 is equal to AS minus AS prime or AS2. That's definitely like the same answer. AS minus AS for flange times Fy times D minus A over 2 this time, because the arm is a D or A over 2 this time, because that's related to when you enter to the domain of web. But here is H of F just in the flange part. And then the only unknown in this equation is A. You can calculate A base of this summation of forces goes 0. And as soon as you have A, you can easily calculate the MRW, MNW, because A is known both sides. From either of these equation works. And then Mn is equal to Mn for flange plus Mn for, or Mr resistant moment is MRF plus MRW. So let's approach the problem. So resistant moment related to flange, ASF is the only unknown here. If you just write down this equation, if forces are equal to each other, it just gives us area steel for flange. If you place in the numeric value, it just gives us a numeric value area of steel related to flange is equal to 4.ASF is equal to 4.59 inches square. As soon as we have area for steel, we can simply calculate MRF or MN nominal moment related to the flange part. That's AS times Fy times D minus HF over 2, HF over 2, but that applies to the half of the centroid of flange. So if you replace that with the numeric value, it just gives you 6 over 2, which is flange over 2, HF over 26, which is the effective depth, 60,000, which is yield strength, and that's ASF replaced directly there. It just gives us a MRF, MNF nominal moment, resistant moment related to the flange part is equal to 6330 inch kilopounds. Likewise, as soon as you have the area for ASF, which is 459, you can replace that in the equation like when you solve it like for double reinforced concrete. It just gives you areas AS minus AS flange, area of steel minus area of steel for flange, which is 459 over 85% of A prime C times BW. Don't forget to work with the BW with the web part. And this is definitely web part. It just gives us A, which you already enter to the domain of the web is just 7.30 inches. As soon as you have your A, you can simply replace that in the equation, and it just gives you MR for web or MN web. That's definitely AS minus AS for web. So that's AS for, sorry, AS, my bad, minus AS for flange, and that's definitely AS for web, area of steel related to web, times 60,000 times 26 minus A over 2. It just gives us like 4,079 times 10 cubed inch. We can round it up, and MRW is equal to 4080 inch kilopounds. And definitely resistant or nominal, that's MNF plus MNW. If you want to know what your M nominal moment is, you just need to add them flange plus the flange, or plus resistant moment or nominal moment is equal to flange moment plus a web moment. If you add them up together, it just gives you the total value, and which is 10,410 inch kilopounds. That's our nominal moment capacity, and if you just multiply that by phi, which is 0.9 for flexural ductile member, that gives you the design moment of 9,369 inch times kilopounds. Just need to, we are done with the problem, we just need to see if we are in our ductile or not. So the very first, we have two ductility check from ACI code, minimum and maximum. So ACI, American Concrete Institute, ACI 318 version 2019 gives us the row minimum should be maximum of these two terms, and if you based off your F prime see a specific strength of concrete, which for our case is 3000, so definitely we are in the first, we are in this part, so this part is controlling Fy over 200 over Fy, which is 200 over 60,000, which is our Fy, and it just gives us 0.0033. That's our row minimum. Available row should be higher than this amount. And let's see what our row density of steel is. AS, which is 6 times number 10 bars over BW times D. Don't forget, when you're working with density calculation of steel, just work with the main part, which is the depth. Depth is the scaffold of the structure. So just go for BW 762, which is 6 times inches squared for number 10. It just, and over BW again, BW times the effective depths. And if that's if you do the math, it just gives you 0.029. That's definitely higher than 0.033. So we are ductile. So we meet the requirement for the minimum ductility. So it means our steel is not a cosmetic steel in concrete. We just jump to the ductility table based off the grade of our steel. So we have grade 60, and C over D should be smaller or at least equal to 0.375. So C is A over beta 1, beta is 0.85, which is the coefficient for F prime C. So if you calculate our C, or distance from the top of the section, that's our to the neutral axis, that's 8.39. It just comes from here. C over D for grade number 60 steel should be C over D for grade 60 should be less than 0.375. So 839 over 26, which is our effective depth, is 0.32, and that's definitely smaller than 8.39 over 26 is equal to 0.32. That's smaller than 75. So our section is ductile. If our section is ductile, we are allowed to use a reduction factor of phi for flexural member. That's all. We'll solve more problem. Thank you.